modern Russian Su-34 strike fighter screams across a contested tree line, carrying not a $1 million satellite-guided munition, but a rusted, unguided FAB-500 iron bomb forged when Leonid Brezhnev was in power. The West long ago relegated unguided gravity bombs to the dustbin of tactical history, treating them as severe liabilities that force expensive aircraft into the jaws of modern air defense networks. Yet, the Russian Aerospace Forces deliberately structure a massive portion of their modern tactical doctrine around this chaotic, seemingly primitive weapon. This is not merely a desperate improvisation born of supply shortages. It is the culmination of a 70-year engineering philosophy that insists the brain belongs in the bomber, not the bomb. To understand why a 21st century superpower willingly embraces dumb munitions in an era of microchip precision, you have to look backward. You have to look at the genesis of Soviet strategic and tactical aviation, specifically the aircraft that laid the unguided foundation the Russian military still relies on today, the Tupolev Tu-16 Badger. The Tu-16 didn't just carry bombs, it carried a mathematical and doctrinal framework that locked Soviet and later Russian aviation into a very specific, highly dangerous way of waging war. If you enjoy detailed deep dives into military engineering and strategy, subscribe to the channel. I've got a lot more planned. The Western approach to dropping gravity bombs changed fundamentally in the late 20th century. Air forces realized that atmospheric variables, human error, and the sheer unpredictability of cast iron meant that unguided bombs missed more often than they hit. The Western solution was to put the intelligence into the munition. Laser seeker heads, GPS receivers, and movable tail fins were strapped to dumb iron, creating precision-guided munitions, PGMs. The aircraft became a mere delivery truck. The bomb did the actual flying. The Soviet Union, however, looked at the exact same problem of gravity bomb inaccuracy and arrived at a completely inverted solution. Instead of making the bomb smarter, they decided to make the aircraft's navigation and computing systems infinitely more precise. If you could calculate the exact airspeed, altitude, barometric pressure, wind drift, and ballistic trajectory perfectly, a completely dumb chunk of iron would land exactly where you wanted it to. This philosophy was hard-coded into the Tupolev Tu-16 Badger, which took its maiden flight in 1952. The Tu-16 was the Soviet Union's first deeply successful swept-wing jet bomber, and it was a masterpiece of brutalist, pragmatic engineering. Tupolev's design bureau was tasked with matching the capabilities of the American Boeing B-47 Stratojet, but Andrei Tupolev flatly refused to copy American design philosophies. Where Boeing used a flexible, shoulder-mounted wing that flapped in the turbulence, Tupolev demanded a rigid, stiff wing swept at an aggressive 35 degrees. This rigid wing was incredibly strong, allowing the Tu-16 to handle aggressive maneuvers and brutal weather conditions that would overstress Western bombers of the era. But engineering always demands a toll, and this rigid structure introduced a severe new challenge. Because the wing was so stiff, it had to be thick, and a thick-swept wing leaves no room for the massive main landing gear required to support a 72-ton aircraft. Tupolev's engineers solved this by placing the main landing gear in large, streamlined pods extending from the trailing edge of the wings. This became a signature Tupolev design trait seen on later aircraft like the Tu-95 Bear and Tu-22M backfire. These pods brilliantly solved the stowage problem and functioned as aerodynamic anti-flutter masses, dampening wing vibrations at high Mach numbers. But this elegant mechanical solution extracted a heavy aerodynamic price. The massive landing gear pods created substantial parasitic drag. To overcome this drag and push the heavy airframe to its top speed of over 1,000 kilometers per hour, the Tu-16 required an astonishing amount of thrust. Enter the Mikulin AM-3 turbojet engines. At the time of their introduction, the AM-3s were some of the most powerful jet engines on the planet, producing a staggering 19,000 pounds of thrust each. They were physically massive power plants, and Tupolev decided to mount them deeply integrated into the wing roots, hugging the fuselage. This placement kept the aircraft's center of gravity tight and reduced asymmetric thrust issues if one engine failed. However, placing two massive, heat-generating, rapidly spinning turbines right next to the fuselage created a perilous operational reality. If an AM-3 engine experienced an uncontained catastrophic failure, such as a turbine blade snapping off at high RPM, the shrapnel would instantly slice into the fuselage, severing hydraulic lines, fuel lines, or control cables. Furthermore, the immense thirst of these single-spool turbojets meant the Tu-16 had to carry over 40,000 liters of aviation fuel just to achieve a functional combat radius. The bomber was essentially a massive, rigid fuel tank wrapped around two temperamental jet engines. And yet, all of this engineering, the rigid wings, the drag-inducing gear pods, the massive AM-3 engines, served only one purpose: to carry a payload of unguided iron bombs to a target. This brings us to the operational reality of aiming. Dropping a free-fall bomb from 10,000 meters while traveling at 900 kilometers per hour is an exercise in chaotic physics. The moment the bomb bay doors open, the aerodynamic profile of the aircraft changes violently. The smooth airflow over the fuselage collapses into a turbulent boundary layer, creating heavy buffeting. When the bomb falls into this slipstream, it is subjected to massive shear forces before it even begins its true ballistic arc. To solve this, the Tu-16 relied on the OPB-11R optical bomb sight, working in tandem with the ruby-MM navigation and targeting radar. The OPB-11R was an incredibly complex analog computer. The navigator, sitting in the extensively glazed greenhouse nose of the aircraft, would visually acquire the target. He would input altitude, indicated airspeed, and estimated wind drift into the analog dials. Mechanical gyroscopes would spool up, attempting to stabilize the optics against the buffeting of the aircraft. This requirement forced a massive structural compromise on the airframe. The need for the navigator to physically see the ground necessitated the Tu-16's iconic glass nose. From an engineering standpoint, a glass nose is a nightmare. It creates a massive radar cross-section, it is aerodynamically suboptimal, and crucially, it is a structural weak point for an aircraft that operates in pressurized altitudes. Early aviation plastics and tempered glasses expanded and contracted at different rates than the aluminum airframe, leading to constant pressurization leaks and maintenance headaches. But the real cost of the OPB-11R and its analog brethren was operational. For the analog computer to calculate the drop point of an unguided bomb accurately, the aircraft had to fly completely straight, perfectly level, and at a constant speed for a significant duration before the release point. The gyros needed time to settle. The mechanical gears needed time to align. Every time a Tu-16 crew lined up for a bombing run, they were forced to fly a highly predictable, linear path. In the 1950s, this was an acceptable risk. But as radar-guided anti-aircraft artillery, AAA, and early surface-to-air missiles, SAMs, began to proliferate, forcing a bomber to fly straight and level for 30 seconds was tantamount to signing the crew's death warrant. The Soviet engineers knew this, but instead of shifting doctrine to guided bombs that could be tossed from erratic, evasive flight paths, they doubled down. They believed that if they could just make the bombing computer faster, they could shorten the vulnerable straight and level run. This relentless pursuit of mathematical perfection for unguided weapons is the direct lineage that leads to the modern Russian SVP-24 GFES targeting system, the digital ghost of the Tu-16's analog sights. The SVP-24 is a specialized navigation and targeting complex retrofitted into modern Russian strike aircraft like the Su-24M, Su-25, and Su-34. The VKS touts the SVP-24 as a revolutionary system that turns dumb iron bombs into precision weapons. In theory, it is an engineering marvel. It completely eliminates the need for the greenhouse glass nose of the Badger era. Instead of a navigator looking through optics, the SVP-24 ties directly into the aircraft's central air data computer. It constantly ingests telemetry, the exact GPS-GLONASS coordinates of the aircraft, pitch, roll, yaw, true airspeed, barometric altitude, and ambient air temperature. It compares this data against a preloaded digital library of bomb ballistics. The system continuously projects a continuously computed release point, CCRP, onto the pilot's heads-up display. The pilot simply flies the aircraft toward the target, holds down the weapon release button, and the SVP-24 computer physically holds the bomb in the bay until the exact microsecond the mathematical parameters are met. Then, the racks release, and the unguided bomb falls. Russian officials have historically claimed that the SVP-24 allows unguided FAB-250 and FAB-500 bombs to hit within 3 to 5 meters of a target from altitudes of 5,000 meters. If true, this implies precision on par with a Western JDAM, but for a fraction of the cost, utilizing massive stockpiles of Soviet-era munitions. But theoretical engineering and the muddy, turbulent reality of combat are rarely the same. So, after seeing how it actually performed, do you think the design approach was worth it? Let me know in the comments. The flaw in the SVP-24 system, and the entire doctrine inherited from the Tu-16, is that it assumes physics can be perfectly modeled. It cannot. The SVP-24 calculates the release point with extraordinary digital precision, but once the bomb leaves the ejector rack, the aircraft's computer has absolutely no control over it. A Western JDAM uses GPS and an inertial measurement unit to continuously adjust its tail fins all the way to the ground, actively fighting wind shear and atmospheric density changes. The Russian unguided bomb is a ballistic prisoner. Furthermore, the munitions themselves betray the math. A FAB-500 M62 is a 500-kilogram high-explosive gravity bomb. These bombs were often cast in massive Soviet foundries decades ago. The manufacturing tolerances of cast iron are not aerospace grade. One bomb might have a slightly thicker casing on one side. Another might have a small burr of metal on a tail fin. Another might have a thicker coat of anti-rust paint. When you drop an object from 5,000 meters, these microscopic asymmetries matter. A slight aerodynamic imperfection on a tail fin will catch the supersonic slipstream and induce a slow spin. By the time the bomb travels 5 kilometers vertically, that tiny wobble translates to a miss radius of 30, 40, or 50 meters. Against a reinforced bunker or a specific bridge pylon, a 50-meter miss is as good as a mile. To compensate for the aerodynamic realities of cast iron, Russian pilots are forced to make a terrible choice. If they drop from high altitude to stay above the range of man-portable air defense systems, manpads, and short-range AAA, the unguided bombs scatter wildly due to wind and manufacturing defects. If they want true precision, they must descend beneath the cloud cover, often dropping to altitudes of 1,000 meters or less to visually acquire the target and minimize the bomb's flight time. This brings us right back to the fatal flaw of the Tu-16 Badger. To get accuracy out of the SVP-24 system, the pilot must fly low, and they must fly perfectly straight and level for the final moments of the attack run so the computer can calculate the release. In the skies over Syria, where the VKS faced insurgent forces with virtually no sophisticated air defense networks, this doctrine worked beautifully. Russian Su-24s and Su-34s orbited at medium altitudes. The SVP-24 crunched the numbers in a permissive environment, and dumb bombs rained down with devastating, if not pinpoint, effect. The Russian Defense Ministry used this campaign as absolute proof that their philosophy, putting the brain in the plane rather than the bomb, was economically and tactically superior. But when this exact same doctrine was imported into contested airspace against a peer military operating dense, layered air defense networks, the results were catastrophic, forcing a $40 million Su-34 strike fighter to fly a predictable, level path at low altitude just to deliver a $500 chunk of rusted iron is a gross miscalculation of risk. Modern radar-guided SAM systems and advanced manpads effortlessly calculate the flight path of an aircraft attempting a straight and level bombing run. The very avionics system designed to make the aircraft lethal became the operational anchor that doomed dozens of airframes. The visual reality on the flight line highlights this jarring contradiction. You will see a technologically advanced Su-34, equipped with titanium armor, advanced electronic warfare pods, and phased array radars, being loaded by ground crews with dull, heavily corroded FAB-500s that look like they belong in a museum. The ground crews have to carefully set the mechanical nose fuses, ensuring the arming wire doesn't snag on the advanced pylons. It is a collision of eras, a modern digital sword swinging a Stone Age club. This operational friction eventually forced a doctrinal pivot, though not a complete abandonment of the underlying philosophy. Recognizing the unsustainable attrition rates of flying strike fighters directly over heavily defended targets to drop gravity bombs, Russian engineers rushed the UMPC, Universal Module for Planning and Correction, into widespread service. The UMPC is, in essence, a crude but highly effective glide kit strapped onto those same old FAB 500 and FAB 1500 dumb bombs. It features pop-out wings and a basic guidance system. By giving the bomb wings, the aircraft can release the weapon from high altitude and high speed, dozens of kilometers away from the target, staying out of the lethal engagement zones of short and medium-range air defenses. This adoption of glide bombs is a tacit, ironclad admission that the Tu-16's foundational doctrine, the idea that a brilliant aircraft can overcome a dumb bomb, has finally reached its absolute limit in modern contested airspace. Yet the DNA of the Tu-16 refuses to die completely. The Badger itself left a legacy that stretches far beyond the Soviet Union. The Chinese People's Liberation Army Air Force, PLAAF, operates the Xi'an HE-6, which is a direct, heavily modernized, license-built derivative of the Tu-16. While modern HE-6 variants like the HE-6K have finally deleted the glass navigator's nose in favor of large radar radomes and rely heavily on long-range cruise missiles, the underlying airframe, the rigid 35-degree swept wings, the landing gear pods, the deeply buried engine roots, remains fundamentally unchanged from Tupolev's 1952 blueprints. The central conflict of Russian bombing doctrine has always been a battle between economic pragmatism and operational survivability. The Soviet Union forged millions of gravity bombs because they were cheap to mass produce in preparation for a total war. They built incredible aircraft like the Tu-16 and developed complex mathematical sights and systems like the SVP-24 to make those cheap bombs viable. For decades, the math almost worked. The engineering ingenuity required to make a supersonic jet calculate the wind drift of a cast-iron sphere is genuinely staggering. But physics is unforgiving, and the enemy gets a vote. By refusing to heavily invest in guided munitions until absolute necessity forced their hand, the doctrine traded the lives of pilots and the loss of irreplaceable airframes just to utilize stockpiles of obsolete iron. The unguided bomb is chaos incarnate. No amount of digital processing in the cockpit can change the aerodynamic reality of what happens when that bomb hits the slipstream. The Tu-16 established the rules of this deadly arithmetic, and modern aviation is still paying the toll. If you like this deep dive, leaving a like helps get it out to other military history fans. Thanks for being here.